Hello all. Now let us talk about the kernel of a homomorphism. Hope I am audible to every one of you. Okay. So phi is a homomorphism from R to R dash. Then if I collect all the elements of the type R belonging to R such that their images are 0, then this set forms a subring, and this subring is called as kernel of phi. And actually we are collecting all the inverse images of this 0 dash. So we can write the same set as phi inverse of 0 dash. Now let us deal with this theorem. Phi from R to R dash bearing homomorphism. H is kernel of phi. Then if I choose any element A from R and take the phi inverse of the set of phi of A, it comes out to be A plus H, or the same as H plus A, where A plus H is the same as H plus A, which is the coset containing A of the commutative additive group H plus. So let us deal with this. So we are first of all considering the set containing all elements X, for which phi of X is the same as phi of A. Means image of X, which is the same as image of A. All such elements we are considering. Now let us deal with this equation separately. So we suppose phi of X is equal to phi of A. What it means itself? So phi of X minus phi of X is 0 dash. 0 dash is the additive identity. 0 dash is the additive identity, as you know, of course, of R dash. Now minus of phi of A, we can say it is minus of phi of A, and I'm just adding it to this. So subtraction means adding additive inverse. This we have written. But minus of phi of A is the same as phi of minus A. Earlier we have seen this. Additive inverse of the image is image of the additive inverse. So we use it. And what we are getting is phi of X plus phi of minus A becomes 0 dash. It itself means phi of X plus minus A is 0 dash, because it is a homomorphism, you know, phi preserves addition. Now its image is 0 dash, means this element must belong to the kernel. So we are saying this belongs to the kernel of phi. And what is kernel of phi? It is H. Set is labeled as H. Now this belongs to H means what? It will be some member of this H. So for some H belonging to capital H, this value will be equal to small h. Meaning thereby X is nothing but A plus H, where H belongs to capital H. So all those elements for which images are equal to phi of A, those elements are nothing but members of A plus capital H. So we have shown here that phi of X is equal to phi of A itself, means X is a member of A plus H, the coset of H. So phi inverse of phi of A means this set is nothing but A plus H. But it is a ring, and ring, you know, it is commutative for addition. So addition is commutative. So you can write it as A plus H is the same as H plus A. So this particular set is nothing but A plus A, but it in turn is the same as the right coset also, H plus A. I suppose you followed the proof. Anybody wants to ask anything? Followed the statement? Okay, if not, all right, only one response. All right, I would like to go with that. See, what I'm doing is I want to show that phi inverse of phi of A. What I mean by phi inverse? Inverse image of the images of A. So can't we take all those elements whose image is the same as phi of A? That is what we have done. So image of X is the same as image of A. When I'm saying X is a variable, and when I say A is a fixed element. So all those elements whose image is the same as image of A, all such elements we are collecting. Now we are just using our algebra. Phi of A is brought to this side. Next, minus phi of A I can write as plus of minus phi A. Next, minus phi of A I can write as phi of minus A. Why for? Because I know this result. Image of the additive inverse is the additive inverse of the image. So this result I have used. Further, phi being homomorphism, you can take this way. Phi of x plus phi of minus a. You can combine as phi of x plus minus a. And you are watching that the image comes out to be 0 dash. Now, whenever the image comes to be 0, we say this member is a member of kernel. So x plus minus a is a member of the kernel. But kernel we are labeling as h. So this element belongs to h. Now this element belongs to H means what? H is a set. H is not itself some element. H is some set. So H being some set, you can have some element of H which will be equal to this. So you have written X plus minus A is equal to H. Now transfer this minus A to that side. You get X equal to A plus H. And H belongs to capital H. So what this means, X is equal to A plus some element of capital H. And every time you take X of this pattern, you will be getting X belonging to A plus H. Means that whenever phi of X is the same as phi of A, X is a member of A plus H. So if I collect all such elements, then it will form coset. But left coset and right coset, they are equal if the addition is commutative. So that is what we have written. And thus this set is nothing but A plus H, which is the same as H plus A. Followed my point? Okay. So I hope we'll read it once again and try to get the concept. All right. I would like to proceed then. This is one more very important result. Last time we have underlined this result. It's a corollary. A ring homomorphism phi from R to R dash is a one-to-one map if and only if kernel of phi is singleton 0. So similar result we have already seen in vector spaces also. The map is 1, 1 if and only if its kernel is singleton 0. So let us go for the proof. Phi is a ring homomorphism. Ring homomorphism means it preserves addition and multiplication. Let us begin with phi is 1, 1. So let us consider phi is 1, 1 map. What 1, 1ness means? Whenever images are equal, the pre-images are also equal. So phi of x equal to phi of y implies x equal to y. Now what I want to show that kernel is singleton 0. So I am interested in kernel of phi. So before going ahead, one more property of homomorphism we are highlighting. What is that property? Phi of 0 is 0 dash. 0 of the domain is mapped to the 0 of the image. Okay. So x belonging to kernel of phi will mean that phi of x is 0 dash. But already you have stated that phi of 0 is 0 dash. Now you are assuming phi of x equal to 0 dash. 0 dash is the same, so we will equate them. Phi of x equal to phi of 0. But you said phi is 1, 1. Whenever images are equal, the pre-images are also equal. Will mean that x equal to 0. So whenever you start with x belonging to kernel of phi, you will be getting x equal to 0 only. Means kernel contains only singleton 0. Followed the proof? Followed? Okay. I would like to repeat. 1, 1 ness we are using. Phi is 1, 1 means whenever images are equal, the pre-images are also equal. We know that 0 is mapped to 0 dash. Now we are considering x belonging to kernel of phi. X is any random number. So phi of x is 0 dash. So these are two 0 dash. 0 dash is one and the same. So we equate them. We got phi of x equal to phi of 0. So we got two images equal. Means the pre-images also must be equal. So x must be 0. Means whenever we start with x belonging to kernel phi, we will always get x equal to 0. Meaning thereby kernel phi has only singleton 0. Followed now? Okay. Now I would like to proceed. All right. I start with kernel of phi equal to singleton 0. And now I want to show that my function phi is a one-to-one map. What I said, kernel of phi has only one element, that is 0. And to show phi is 1, 1, we always start with images are equal. So we consider phi of x equal to phi of y. Now how to proceed? So bring this phi of y to the left side. So what you are getting? Phi of x minus phi of y is equal to 0. Actually, I should have given dash here. Please correct it. Please correct. This 0 is from the range set. So it must be 0 dash. So what you are getting is phi of x minus phi of y equal to 0 dash. But minus phi of y you can write this way. Phi of x plus minus of phi of y. But minus of phi of y is the same as phi of minus y because it is homomorphism. And lastly, you are watching that phi preserves addition, so I can write it as phi of x minus y. So what I'm getting, x minus y has image 0 dash. So x minus y belongs to kernel of phi. Its image is 0 means it is a member of kernel. But x minus y belongs to kernel and your kernel is having only one element 0. Means x minus y must be 0. So x is equal to y. Thus you get phi is 1, 1. Is it okay, Pradnya?
Yes, ma'am.
Okay, Suvarna got it?
Yes, ma'am.
All right. Anjali? So the document is already sent to you. I hope you'll take proper care of it. Try to get the thing done. And now we are in factor rings or quotient rings. What is meant by factor rings? So we will be collecting all additive cosets of H. Just go on collecting all additive cosets of H. And then the set of all cosets is nothing but R upon H. So already we have written it over here. I think I have written it here somewhere. No, it is not there. Okay. Okay, doesn't matter. So what we are going to do is we are collecting all the cosets and the set of all cosets is nothing but R upon H. How to define binary operations on it? So A plus H and B plus H. How to add them? So it will be A plus B plus H. How would you add two, multiply two cosets, A plus H and B plus H? Multiplication will be AB plus H. So, yes. Okay, here it comes. See, last time we dealt with this example. We are in modulo 5 set. We are talking about 5 from Z to Z5. And how is it defined? So if you take any integer m, phi of m is nothing but the remainder when divided by 5. Meaning m congruent to r modulo 5. This r we are taking here. Now, we are talking about the set H, that is kernel of phi. What will be kernel of phi? So you are watching here. Kernel of phi is nothing but the set of all 5n. Multiples of 5 leave remainder 0. That is why H is nothing but the set 5n. Now, you are watching. We just tried to collect the images under phi. Phi of 0, 0, phi of 1 is 1, phi of 2 is 2, phi of 3 is 3, and phi of 4 is 4. Why 4? Because they leave these many reminders when divided by 5. Yesterday itself we have discussed this. Now if I take 6, what will be the image of 6? So 6 divided by 5, remainder is 1. So phi of 1 is the same as phi of 6 that you are watching. If I go for phi of 7, the image is the same as phi of 2, that is 2, and so on. So I suppose you got me. We selected set H as the set of all multiples of 5. Now just go on constructing the cosets. How do you construct coset? Select integers from Z and add it to the set that constitutes of a set of some elements. You call it as coset of H. Now presently, if you add 0, all the elements remain the same. If you add 1, yesterday itself you prompted me these elements. Then if I add 2, I'm getting these elements. By adding 3, these are the elements. By adding 4, you get these many elements. And what you observe, last time we have counted this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. Next, you go back from 0, 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10, and so on. So all the integers are covered here. So these are the only cosets of H, different cosets of H. So we collect all those cosets. First was 0 plus H. Second was 1 plus H. Next is 2 plus H, then 3 plus H, and last 4 plus H. All those cosets have collected under a set, and we are labeling it as Z upon NZ. Do you agree? What we have written? Z upon H. And what is my H? H is nothing but NZ. So we are directly writing it as Z upon NZ. How many of you followed up to this? Okay, only yes, yes, yes. Pradnya, what we have done, Gauri? We are simply collecting the cosets. That's all. How many distinct cosets are there? Five distinct cosets are there. First was h itself, meaning 0 plus h. Second was 1 plus h. Then was 2 plus h. Then 3 plus h. And then 4 plus h. If you go for 5 plus h, it will give you 0 plus h back in hand. You can try. So I suppose you followed me that it is the set of all cosets. And because it is just making compartments of this Z, all elements of Z are comparted here. These are just kind of compartments. So we call it as factor ring. So we call it as factor ring. But for being a ring, only set is not important. It needs operations also. So how these operations are defined? Let us go ahead. You take any two elements out of this. How to add them? You just add the elements here, A plus B. So 4 plus 2, but we are in modulo 5. So 2 plus 4 modulo 5 is the answer 1. So you got it to be 1 plus h. If you go for multiplication, 2 plus h into 4 plus h, what will be the product? So we go with 2 fours are 8. Again, we are in modulo 5 scenario. So 8 divided by 5 will produce 3 as the remainder. And that is why we have written this as 3 plus h. Did you follow me?
Yes, ma'am.
Okay. So this way we are defining. So let us be back to our document. What this document tells you. Again, let us see the additive cosets of H form a ring R by H whose binary operations are defined by A plus H plus B plus H equal to A plus B plus H and A plus H times B plus H will be A times B plus H. So this way with these operations this R by H forms a ring. Now let us move ahead. The last statement of the theorem says the map mu from R by H to phi of R defined by mu of A plus H equal to phi of A is an isomorphism. What is an isomorphism? So basically it must be homomorphism. Then 1,
Bijective.
1. Yes, of course, bijective. 1, 1 and on 2. So we need that. So let us go for the proof. See, phi from R to R dash bearing homomorphism with kernel H. So R by H, the factor set, will be of the kind A plus H, where A is taken from R. Now they have given us this definition of addition, and this addition you can watch here will be binary because the answer is back in the set, associative and commutative. So I need not prove this. It is just hereditary one. Now the question of additive identity comes. So H itself is 0 plus H. So it will be the additive identity because it being kernel of that particular, it becomes the additive identity. Also for A plus H, there is minus A plus H. So that if I add them, I'm getting this at 0 plus H, which is H itself. Means minus A plus H is the additive inverse of A plus H. Followed this? The additive inverse of A plus H is minus A plus H. Why for? Because there are some vanishes, it becomes 0 plus H. So I'm getting back my identity. Okay. So all the 5 properties got satisfied. Binariness is there, associativity is there, identity is there, inverse is there, and lastly commutative properties also in addition satisfied. So it becomes an abelian group. It's an abelian group. Now let us talk about multiplication, because with multiplication I want binariness also. Then I want the multiplication to be associative, and lastly I want multiplication to be distributive. So let us go one by one. So to show multiplication is well defined. Beforehand definition produces some meaningful thing I need to show. So we because we are writing a plus h multiplied by b plus h. I mean set multiplied by set. So I need to show that all the elements are there. So this is our responsibility. So for that, what we are doing, we are taking h1 and h2 members of capital H. So a plus h1 will be in a plus h, and b plus h2 will be in b plus h. So instead of writing the set, I can talk about the element. So we have selected that elements from here. Now let us multiply the elements. Multiplying elements is quite usual. You cannot multiply two sets, is it? So C equal to product of these two. So I have expanded it, you can see. Now how this particular sets are concerned, they are concerned with phi, homomorphism. So let us apply phi on it. So phi of C equal to phi of AB, this we want. So let us go. We started with phi of C. This will be phi of this whole sum. Now phi is homomorphism, so it will split the addition. Phi of first plus phi of second plus phi of third and plus phi of last. Again, product also you can separate. So phi of AB, because I want AB, I'm keeping it as it is. We didn't open. But here you need to open it. Phi of A into phi of H2. Phi of B into phi of H1. Phi of H1 into phi of H2. Now what are those H? They are members of capital H. What was capital H? Kernel. What kernel means? Image is 0. So phi of H2 is 0 dash. Phi of H1 is also 0 dash. So this is 0. Here I'm getting 0. This one is also 0, and here also I'm getting 0. So what happens? This whole part goes off and we are simply left with phi of AB. So what you started with, C as this product, and you have shown that phi of C is the same as phi of AB. I suppose you followed me. So what will happen? What is C? It is the inverse image of phi of AB. So C belongs to phi inverse of phi of AB, but this is nothing but AB plus H. So C belongs to AB plus H. We cannot directly talk about set into set. We have to go by element wise, and that is what we have shown. Instead of dealing with the sets, we have taken representative element, we multiplied, applied phi on it, and we reached to this result that C belongs to this coset. Means multiplication is well defined. Now, the associative and distributive properties, they will follow because it is just a part of your R dash. So they follow. So R upon H forms a ring. And what you are getting? Mu from R upon H to phi of R. How we are defining? Mu of A plus H is equal to phi of A. This is a part of the theorem itself. You can see mu from R by H to phi of R. How they have defined? Mu of A plus H is the same as phi of A. And our duty is to show that this particular mu is an isomorphism. So we continued here. We have mu from R by H to phi of R. This is our definition. So basically phi's homomorphism will mean that mu is a homomorphism. Second thing, you are going to the image set. When your codomain is image set itself, it is onto directly. So you got homomorphism also and onto also. Now what is left? Being 1, 1. So for 1, 1ness, what we'll do is we'll go with the kernel. So mu of 0 plus h means phi of 0, which is 0 dash. So directly we are getting this to be phi mu is 1, 1, and thus mu becomes isomorphism. So I suppose you followed this. You might have taken it down. Any doubt regarding this? Yes, please come up. Anybody wants to ask anything? Have you really followed?
Yes, ma'am.
Okay, okay. So I would like to move back then. So we are in factor rings or quotient rings, and this theorem just now we have seen. Okay. Now this example also we have seen just now, z upon nz, and we wanted to show that it is isomorphic to Zn. For that, we have considered this particular n equal to 5, we have taken n in particular for 5. We tried to solve it. Then we considered mu. How mu is defined? Mu of a plus h is phi of a. So in the present case, we have shown that mu of 2 plus h is phi of 2. And phi of 2 is nothing but 2. You may go with mu of any of these. So directly you can tell me what will be mu of this particular 0 plus h. It will be phi of 0. And phi of 0 is what? 0. Mu of this particular will be 1. Mu of this will be 2. Mu of this is 3 and mu of this is 4. So what we are getting in hand? We are getting Zn. The images are 0, 1, 2, 3 and 4 only. So what is this set with us? What this set is known as?
Z5.
So we got Z5 and that is what we are interested in. So here itself we are saying Z upon Nz is isomorphic to Zn. So taking n equal to 5, we have shown it, how it becomes. Why for n equal to 5? Because it creates a set with 5 elements only. So becomes easy to visualize. And for the purpose of visualization, we did so. Okay. Anything you want to ask about this? Yes, come up. If no, then I have to proceed for ideals. Ready for ideals? Okay. So the basic concept of ideal, you see, an additive subgroup capital N of a ring capital R. N does not stand for this natural number set. Neither R stands for real set. R stands only for a ring and N is taken as a letter or a symbol for a subgroup. That's all. You know, subgroup, when I say it is itself a group. Please rejoin. Please rejoin. So N is not the set of natural numbers, this we mean to say.